This is the second lecture of Applied Microeconometrics, and today we're going to look at quantile regression. But before we are going to look at quantile regression, it is better to start with quantiles themselves. Quantile regression is, of course, all about quantiles, and I'm pretty sure that most of you must have heard about quantiles before. And if you have never heard about quantiles before, well, then I'm pretty sure that you have ever heard about things as medians, quartiles, decimals, and percentiles. So well, I think that everybody knows that if you're going to look at the median, well, more in particular at the moment that you're going to look at the sample median, then what you typically do is that you're first of all going to, well, sort the data, and then you're going to take the observation that is then based on the sorted data exactly in the middle, and that's going to be your median. Well, it is exactly the same thing with respect to these other things. Well, in order to make this a little bit more mathematical and to look at the analytics, what I'm going to do is that I'm going to introduce here a sequence of random variables, yi, and I is going to run from 1 till n, and they're going to be iid. I'm going to assume over here that y1 is going to be continuously distributed. That's not really necessary at the moment that we're going to look at quantiles, but generally things become much more difficult at the moment that we are going to look at discretely distributed random variables. In the case of quantiles, at least the notation is going to be much more difficult, and therefore I've chosen to, well, just assume that y1 is going to be continuously distributed, and then later on say what is going to happen at the moment that we are going to have a discrete distribution. Then the population tauth quantile of y1, well, look at the notation over here. What we are going to have over here is a q, and q is this mathematical q that we have over here, and then we have a subscript tau. We will later on see what that actually means. And here we have, between parentheses, we have y1, in order to indicate that we are going to look here at the quantile of y1. By the way, that's of course also of all the other yi's, because of the fact that we have here this iid assumption. And also take into account that this notation is quite like the notation that you already know of from a mean, because remember that a mean is usually a mathematical e and then y1, and here we now have a q. And a population quantile is always going to be, well, satisfying the following. It's going to be exactly that number that makes the probability y1 is smaller or equal to that number equal to this tau that we have over here. Well, and then tau equal to half means that we're going to look at the median. Tau equal to 0.25 is the first quartile, etc. In addition to that, we also see here that at the moment that we're going to look at this probability, well, this is actually nothing else as the distribution function of y1. So we can also write it as the distribution function of y1, evaluated in our quantile. And then we can use the fact that we have here a continuously distributed random variable. So therefore, this distribution function is strictly upward sloping, it's monotonic. So therefore we can take the inverse, and then we actually see that the quantile is actually nothing else as the, well, inverse distribution function of y1 evaluated in tau. Well, later on I will show you what actually the, well, interpretation of that is. We will look at the graphical representation, but before I'm going to do that, a little bit more of mathematics. Of course, we can look at this representation that we've over here. This is the easiest one. But you can also look at another representation, and that's this one that we have over here that you actually see quite often in the literature. This is actually a representation that even holds in the discrete case, and that says that the quantile can be seen as an argument that is going to minimize this criterion function that we've over here with this somewhat ugly looking criterion function that we have over here. And I can even say that this, well, minimum that we have over here is going to be unique. Well, the question of course arises, why is this so interesting? Well, this is interesting for estimation. And the reason behind that is because of the fact that, well, generally we cannot calculate these quantiles. As econometricians, we cannot calculate these quantiles. We can only do that at the moment that we know the distribution function of y1, but that is data, and typically we do not assume as econometricians that we know the distribution function of the data. Otherwise, nothing is necessary anymore. So therefore, we do not know this distribution function, but we would like to, of course, estimate this thing that we have here at the left-hand side. Question arises, how can we estimate? Well, that's not directly clear, but from this, what we could say is that here we have an expected value. And we do know that expected values, what we usually call population means, can be always estimated by their corresponding sample mean. How do we do that? Well, that's always the same. We do not take expectations, but we get summations, and we are going to sum over all the observations that we have, and we divide by n. Then we get this thing that we have over here, and that is now going to be our sample mean that corresponds to that thing that we've over there. We know from the law of large numbers that this thing that we have over here, of course, in general is going to be different from that thing that we have over there, because of the fact that we should take into account that, well, this is based on a random sample. So it would be really strange if we would exactly get the mean over here. So generally this is going to be different, but we should take into account that if n goes to infinity, then this thing that we have over here is going to converge to that thing that we have over there. That's, by the way, not just for one particular level of Q, but it's for any level of Q that we can actually think about. So that implies that what we could say is that, well, if we see this thing that we have over here as a function of Q, well, actually we see it as a function because of the fact we minimize with respect to that function, then we can see this also as a function. What we can say is that this function, of course, is different from that function that we have over there for any level of Q. But if n goes to infinity, then these two functions are going to be exactly the same. Well, that's pretty nice, because of the fact that then what we have is that we have essentially a function over here, which we do not know of. But what we do know about this function is that at the moment that we're going to minimize it, we are going to get our quantile. Well, this function, well, it's actually generally also unknown, but at least we can estimate it. And what we do know is that even though this function is different from the function that we had in the previous slide, at the moment that n goes to infinity, the functions are going to be exactly the same. But if the functions are going to be exactly the same, so are going to be their minima. So therefore we are going to have the following. What I just said was that this function over here is going to converge in probability to that function over there. But we do know that if they are the same function, so the minima should actually also converge to each other. But now you should realize that what we have here at the left is exactly equal to, well, what we define here as Q hat, our estimator. And what we have here at the right is exactly equal to the quantile that we wanted to estimate. So therefore, if we are going to, well, define this estimator as being this thing that we have here at the right hand side, well, then it's not so difficult to understand that this Q hat is going to be a consistent estimator of the Q that we have over there. That is something that we're going to use many, many times. Take into account that this actually looks a little bit difficult to do in, well, in the simple way in which we simply are going to look at quantiles. Then we do exactly the way I started with. The moment that you want to estimate the median, we just take the value in the middle, but that's actually exactly this thing that we have here as well. Well, what we should realize now is that, well, before I'm going to do anything else, what I would like to do is that I would like to rewrite this thing a little bit, because of the fact that in the literature, typically we don't write it in this format that we have over here. What we should realize is that we first of all can substitute in the m tau that we had the previous slide, so this thing over here. Going to do that, and we're going to get this thing over here, and then we can even rewrite it a little bit more, because of the fact that we see that this part of the summation is only different from 0 in the case that yi is larger or equal to q. So therefore we can also use a separate, say, summation for only those observations which yi is larger or equal to q. And here's the other way around. This is only different from 0 at the moment that y is smaller than q. So there we can also look at a summation over yi smaller than q. So therefore then we can minimize this thing that we have over here in order to get the quantile. This all looks fine. However, we should take one thing into account, and that is that, well, I have now proven that we have a consistent estimator, but one thing that I have done in the proof was that I took one particular thing for granted, and that was this statement that we have over here, that, well, this actually is a unique minimum. So that we have still to prove. How are we going to do that? Well, what we need to do then is that we first of all have to look at this, well, mean that we have over here. Well, this is a population mean, so then that means that we're always going to get an integral. It's going to be the integral over, well, all the potential outcomes of y1 that we denote here as the support. We denote it by the calligraphic y that we have over here, of course, this function that we have over there, and then multiplied by the density function. In this case, we can use the density function because the fact that y1 was assumed to be continuously distributed. Then we substitute in m tau, then we get this thing that we have over here. We can rewrite this a bit. First of all, I'm going to make this ugly looking integral even a little bit more ugly by taking the, well, density into the parentheses. So what we have done is that I can multiply this by the density function and also this by the density function. We get this even longer integral now over here, but now it's an integral of a sum, that's sum of integrals. So therefore I can also write it like these two integrals that we have over here. Now focus first of all on the first integral. Even though this is an integral over the whole support, this is only going to be different at the moment that y is larger or equal to q. So therefore we could also, in fact, well, integrate here from, not just from over the whole support of y, but just from, say, q, well, to above, to the, well, the supremum of this support that we have over there. So therefore I can rewrite this in this way that we have over here. The nice thing is that I then do not have this indicator function anymore. And I can do exactly the same thing with respect to this one. Well, this is an integral for over, again, the whole support, but it's only different from 0 at the moment that y is smaller than q. So therefore, instead of, well, integrating over the whole support, we can as well integrate from the infimum up till q. Then we should realize that then if we integrate over here, well then, well, all the points that we have over here with respect to y, they're larger than q. So that means that this is going to be positive. So we can also write this as y minus q. Here's the other way around. Here we integrate over values that are smaller than q. So therefore y is always smaller than q. So that means that, well, this is always going to be negative here in between the absolute value. So we can better write it as q minus y. So then we get all these things over here. Now the next trick that we're going to use is partial integration. We know from high school that at the moment that we have to calculate the primitive of the multiplicative of two functions, fx and gx, well then we can write that as the, well, multiplicative of fx multiplied by the primitive of this gx, which is, well, capital Gx, minus the primitive of the first order derivative of f multiplied by this, again, this capital Gx. This is a trick because of the fact that in some cases, well, taking the primitive over here is much easier than the primitive over there. The trick then always is that we should find a function that is relatively easy to get a primitive of. In our case, the candidate here is of course this thing that is over here, the density function, because we do know that the primitive density function is always the distribution function. I'm going to make it a bit more difficult because of the fact that I'm going to realize over here that even in the case that we take the first order derivative of this thing that is over here, so not the distribution function itself, but minus 1 minus the distribution function, we get also this density function. So that says that, another primitive of the density function is this thing that we have here in between parentheses. So that implies that what we're going to get is that we're going to get, first of all, minus 1 minus the distribution function over here, multiplied, of course, by y minus q. And then we get here the minus sign, but we have another minus sign here. So therefore we get a plus sign of the integral. We take the first order derivative of y minus q with respect to y, so that is going to give me 1, and then multiplied, of course, again by this, well, distribution, 1 minus the distribution function. So therefore we are going to get all these terms over here. I can do something similar with respect to the second integral, but now I'm going to really use the fact that the primitive of the density is a distribution function. So then what we're going to get is the distribution function multiplied by q minus y, and then we get minus the distribution function, of course, or an integral of the distribution function, and then multiplied by the first order derivative of this thing over here, but that's minus 1, so we actually get another time a plus sign before the integral, and that means, of course, that in total we're going to get now this thing together with this thing over here. Well, then the next thing we can do is that we can then substitute in these things over here. Well, I can claim here that all the terms here are equal to 0. That's first of all because of the fact that if I, well, first of all, evaluate the distribution function in a supremum, well, then I get 1. So I get 1 minus 1, that's equal to 0. And if I'm going to look here at the lower bound, then I get q minus q over here. That's also equal to 0. So therefore this whole thing that we have over here is equal to 0. Well, the same is actually true for this thing that we have over here. If I, first of all, if I evaluate this in q, then I get q minus q, that's equal to 0. And if I evaluate this term in the infimum, then I get a 0 over here. So also this term is equal to 0, that term is equal to 0. So in the end, what I get is just these two terms that we have over here. Now what we need to do is that we are not that much interested in this mean that we have over here, but we wanted to minimize that mean. That means that we are going to look at a first order condition. That means that I'm going to take the first order derivative of this thing that we have over here and set it equal to 0. The question, of course, arises, how can I take a first order derivative of something that contains an integral? Well, for that we have Leibniz rule. Leibniz rule says that suppose that we have a particular function, this function that we have over here that is related to an integral that depends on x. It depends actually in 3 ways on x because of the fact that the gxy function that we have here inside the integral actually depends on x, but also the upper and the lower bounds, they depend on x. Then Leibniz rule says that first of all what we're going to do is that we're going to differentiate within the, say, integral. So we're going to get this first order derivative over here, we integrate over the whole function, and then we get, in addition to that, we get the first order derivative of the upper bound, this bx over here. That's bx and x multiplied by g evaluate x and the upper bound bx minus the first order derivative of the lower bound evaluated in gx and ax. Well, how are we going to do that in this particular case? Let's first of all look at this part over here. Realize that what we need to do here is take first order derivatives with respect to q. There's nothing within the integral that actually depends on q, so therefore we can completely ignore this part over here. And that's actually also true with respect to the upper bound. Also that doesn't depend on q. So also this part over here, well, we don't have to take that into account, but the lower bound depends on q. It's actually equal to q itself. So taking the first order derivative, so the first order derivative ax and x, in this case is simply equal to 1. So we get a 1 multiplied by, well, here we have a minus 1, of course, minus 1 multiplied by the tau, so this tau that is over here, and then multiplied by, well, this thing evaluated in q, and that's this part that we have over here. And then we get the first order derivative of this thing over here. Well, then again, within the integral, nothing depends on q, so again, this part over here is equal to 0. upper bound now depends on q. It's equal to, well, the first order derivative is equal to 1. So bx and x is equal to 1. And we multiply it by, well, f evaluated now in q. So this thing over here, lower bound again doesn't depend on q. So this part over here is equal to 0. So in total, we're going to get this first order derivative. Well, we can rewrite that a bit. We can first of all get rid of the parentheses here. Then we get minus tau plus tau times the distribution function. Well, and then we get also rid of this, well, part over here. We get a distribution function minus tau times the distribution function. These two terms are going to cancel each other. So finally, we get something relatively simple, minus tau plus the distribution function evaluating q. We have to set that equal to 0. That means, of course, that our solution is going to be equal to the distribution function in q equal to tau. Well, if you take from the left and the right hand side inverses, well, then we immediately see that q is equal to the inverse distribution function evaluated in tau. And hey, that was actually equal to our, say, quantile, our definition of the quantile. Now I've shown that actually, well, minimizing our Cartesian function actually uniquely gives our quantile. Well, if I'm going to go on, I would like to make, well, one particular comment with respect to the median. If you know that the distribution function that we have over here, y1 is symmetric, then in that particular case, it is possible to show, or it's actually not that difficult to show, that the median and mean, they're exactly identical to each other. What does that mean? That means that if I'm going to assume that I have a symmetric distribution, well, then I could actually use the estimator of the median if I would like to have the mean, and the other way around as well. If I would like to estimate the mean, then I could, well, if I actually now say it 2 times the same, but if I estimate the mean over here, then that could actually be used as an estimator for the median as well. Then the question, of course, arises, what is then the best to do in this particular case? Well, that actually depends on the situation. We should realize that a mean has a lower variance. So that is to say that the mean estimator is always going to be more efficient. But you should take into account that the median is more robust against outliers. That's easy to explain at the moment that we're going to look at an example. Suppose that we are going to look at wages. You should realize that wages usually have outliers. That's to say that if you, for example, are going to look at the median or the monthly wage of individuals in euros here in the Netherlands, well, then there are a lot of people that don't make that much. Well, a lot of people make more than, say, 2,000 euros a month. Actually, not that many people make more than 4,000 or 5,000 euros a month. But you should take into account that it's not that strange to see somebody in your data set, at the moment that you have a data set, that makes, for example, more than 10,000 euros a month, or maybe even more than 20,000 euros a month. In the Netherlands, at least, it's not completely impossible, even though these are, of course, outliers. Suppose that you're going to have a data set, and suppose that you only have 100 observations, and suppose that you have been very unlucky in that sense, that you have one particular outlier of somebody making more than 20, maybe even more per month. Suppose that you have a soccer player that makes even more than 50 or 60,000 euros a month. Well, that outlier is going to have a big impact on the mean, of course, because of the fact that what you do with the mean is that you sum up over all the wages and divide by the number of observations. That means, of course, that that has a big impact on the mean. But it doesn't have any impact on the median because of the fact that what you're going to do with respect to the median is that you're only going to look at the observation in the middle, and that actually doesn't change with respect to outliers. Well, now I would like to look at a graphical representation. This is going to be very simple, but later on it's going to be helpful. Here we have on the x-axis we have the different values of y, and on the y-axis we have now the distribution function. Suppose that our distribution function looks like the one that we have over here. Then we could first of all be interested in median. And what we need to do is that we have to start here at 0.5. And then we're going to look at the inverse distribution function. So that means that we walk all the way over here. And this is going to be our median. We can do exactly the same thing with respect to the third quartile, and then we start here at 0.75, and then we walk all the way over there in order to get the third quartile over there. I'd like to go on with another topic, and that is the topic of invariance to monotonic transformations. What we should realize is that, well, doing quantiles could actually be, in many cases, much more difficult than looking at means. And that also means that doing quantile regression analysis is, in many cases, much more difficult than doing, for example, standard regression analysis. However, sometimes it's the other way around. Sometimes it's the case that, well, what could be very difficult with respect to, well, standard regression might be easy at the moment that we're going to look at quantiles, or quantile regression. That has all to do with some particular characteristics that quantiles have that is actually not true for means, and that's invariance to monotonic transformations. Suppose that we're going to look at the stochastic variable z, and z is going to be, well, you could say a derived stochastic variable because of the fact that it's it's equal to the function g evaluated in y, where g is some kind of random function. It's not completely random because of the fact we're going to assume that g is an increasing function. Well, then what we can do is that we can then look at the quantile of z. Well, that's by definition, of course, equal to, well, the value that is going to make the probability that z is small or equal to that value equal to tau. I'm going to use here a little bit of notation. Actually, I could have placed here, of course, the quantile of z, but I now use the quantile of gy, which is, of course, also equal to z. First thing I can do now is that I can use the definition of z, which is, of course, equal to gy, so we can also write this as the probability that gy is smaller or equal to this thing over here. Now I can use the fact that g is increasing, which means that it is invertible. So what I can do is that I can take the inverse here from the left and the right hand side. If I'm going to do that, then I get the probability that y is smaller or equal to the inverse function of g, evaluated now still in our quantile. Well, if we're now going to look at this whole function that we have over here, this whole equation that we have over here, then you should realize that we now have a definition no longer of the, say, quantile of gy, but now actually of y itself. Because now this thing that we have over here is the value that makes the probability that y is smaller or equal to that value equal to tau. So that means that the quantile of y is actually exactly equal to this value over here. Well, then what we can do next is that we can then realize that we can now take the inverse of the inverse function, that's of course g itself, from the left and the right hand side, and then we see that, well, the quantile of gy is equal to g evaluating the quantile. Maybe better to say this means that a quantile of a function is equal to the function evaluated in the quantile. It means, for example, that suppose that we are in a situation in which we would like to look at the, well, the quantile, or maybe we would like to look at the median log income. Suppose that we only know the median of the income itself. Well, then you should realize that then it's not that difficult to get the median of the log income, because then we just take the logarithm of the median income and we get the median log income. Even though this makes a lot of sense, you should realize that this is actually not true for means. We know already for a very long period of time that the mean of a function is not equal to the function evaluated in the mean. This is only true at the moment that y is going to be deterministic, or in the case that g is going to be linear. I'd like now to go on with the asymptotic distribution of the quantile estimator. I'm only going to give here the result. You can actually show that the variance of a quantile, or the quantile estimator, is equal to tau multiplied by 1 minus tau, and then divided by the density function squared evaluated in this quantile that we have over here. That's relatively simple, but we should take into account that if we are going to calculate this thing over here, we can actually not do that. So suppose that you have estimated your, say, quantile in the ways that we have already seen before, and then you would like to calculate the variance of that estimator. Then you should realize that you can actually not directly calculate this thing over here. That's true for two reasons. First of all, because of the fact that we do not know what a quantile is. If we would have known the quantile, why would we actually have estimated it? So here what we could do is that we could say like, well, even though we do not know the quantile, we could of course here substitute instead the estimator of our quantile, which is of course not the same, but well, at least the number of observations is going to be large. Then we are going to get close. Then the question arises, how are we going to be able to know the density function that we've over here? We don't know that either. We might try to estimate it, of course. Well, in the literature there are various ways to do it, and one way to do it is to simply use a parametric form. What we could have done is that we are going to not assume that we know this density function completely, but that we know it up to a parametric form. We could have, for example, assumed that y1 is normally distributed, and then the only thing that we need to do is that we have to then say estimate the mean and the variance. Well, we can do that with standard maximum likelihood of that density that we have over here. And then what we're going to do is that we have the full density, because we do know that based on normal distribution, we know the mean and the standard error, at least if we, at the moment that we have estimators of that, then we actually also know the whole density. So we can get then an estimator of our density simply by evaluating it in the estimated mean and variance. Well, that's a possibility, but it's maybe not a very smart one. And the reason behind that is because of the fact that if you would have known that a particular density has a parametric form, then why would we even be interested in the quantiles? Why would we be interested in trying to estimate the quantiles in the way that we did it so far? Because the way we did it so far was completely non-parametric. If we know already the parametric form of y1, of our thing that we would like to get our quantile of, then there would have been a very much easier way to do it. We should then, in that particular situation, well, if we know, for example, that underlying distribution is normal, then we could have simply estimated the mean and the variance, and then we get the full distribution of our normal distribution, and we immediately then get the quantiles because of the fact that the quantiles are nothing else as the inverses of that distribution function. But the reason why we can actually not do that is because of the fact that we don't want to make any assumption about our distribution. So therefore, why then do it at the moment that we are going to calculate the variance? So therefore, in that sense, it might be better to also try to estimate this density function completely non-parametric. Well, there is a way to estimate density functions non-parametrically, and that's by way of kernel density estimation. I'm not going to talk too much about that. If you would like to know more about kernel density estimation, well, then I would like to promote my next master lecture series, because of the fact that in the next block I'm going to teach kernel density estimation in a course which is called machine learning or data science and machine learning. Okay, let's now look at an application of this. The application I'm going to use here is the March supplement of the current population survey, usually called the CPS or the March CPS, and that's data for the United States. This is going to be a repeated cross-section. Every year in March, people are going to be asked different kind of things, and one of the things that they're asked is the wages. These are actually the wages of the year before. The first time that that happened, the CPS already exists for a very much longer period of time, but the first time that that actually happened, that people were asked about the wages, was in 1976. So that implies that even though I'm going to always use the survey year, that at the moment that I'm talking about 1976, it means that these are wages that were reported for the year. They were reported in 1976, but they were reported for the year 1975. And then we have detailed variables on education, age, region, gender, and race. Well, I'm going to not use them over here, but later on I'm going to use these variables in regressions. Here we are going to mainly look at the distribution of wages among women and men, and more in particular what we're going to do is we're going to look at the quantiles. That's what I've done over here. Here on the x-axis I have the different values of tau, and on the y-axis I have the quantile. So for example, at the moment that we're going to look here at 0.5, then we are going to look at the medians, and we have two different groups here, males, which are well drawn here in orange, and in blue we have the females. Well, based on this, we see a number of different things. First of all, we do see that for both males and females, the quantiles are upward sloping. So this we usually call the quantile function with respect to the different levels of tau. It's upward sloping with respect to tau, both for males and females. Well, we should realize that that's actually always true. It's always the case that actually at the moment that we're going to look at the median, then the median is lower than the third quartile, and the median is of course larger than the first quartile. So therefore we should realize that these things should always be upward sloping. Another way of saying this is that we do already know that quantiles are inverse distribution functions. Distribution functions are upward sloping, so therefore the quantile functions should also be upward sloping. Another thing that we see over here, and that's more particular to this particular application, is that the quantile function for the males is always higher than that of females. Well, that is nothing else as saying that we actually see here that males have higher wages than females. And that's not just true at one particular aspect of the distribution, such as the mean or in our case the median. We do see that males make everywhere a little bit more than females. Well, we'll see that it's maybe not a little bit more later in the next slide, but we do see that males make more than females. That's even the case for the year that we are looking at, 2022. Well, the question now of course arises, now we do see that it's higher here everywhere at the median, but also at the first quartile and the third quartile. Question arises now, well, does it actually differ a lot between, well, the different locations in the distribution? Well, that's here a little bit difficult to see, because it's difficult to see whether this difference is larger than that difference or that difference over there. So in that sense, it's more interesting to look at the following picture, where I have now, well, essentially took the difference between these two things that we have over here. Then we get the following picture, and from this we can, well, draw a couple of conclusions as well. As we already have seen, well, the quantiles of the males are always higher than the quantiles of the females, and now we actually do see that that's somewhere in between, say, 22 and almost 30%. Depending, of course, on where we are with respect to the location. Another thing that we see is that actually along the distribution, well, there is, even though it goes up and down all the time, we do see that there is not such much of a difference up till about, I would say, the third quartile. However, as soon as we pass the third quartile, then we actually do see that even though there it goes up and up and down all the time, that it seems to be increasing. Well, this is usually a phenomenon that we see in many countries, and that is usually called the glass ceiling. The glass ceiling is the phenomenon that, well, it may be possible that the difference between wages of women and men is not so large. We do actually see that it's actually not so small either actually as well, because of the fact that we do see here, even in the year 2022, that, well, men make about, well, this is in log terms, so men make about 20 to 22% more than women. That's quite a lot, of course. But we do see that it's even larger at the top of the distribution, which implies that women, well, actually do much worse at the top of the distribution than at the bottom, or at least at the mean of the distribution, median of the distribution. And this might imply that women have difficulties of climbing up the job ladder, as we see over here. Even though it is immediately clear that we do actually see such a class ceiling effect here for the year 2022, we should take into account that this phenomenon is actually relatively recent. For example, if we're going to look at the year 1976, then we'd see a completely different picture. One thing that we, by the way, immediately see over here is that the average, well, the difference between males and females is here much larger as we have in 2022. That's a thing that I'm going to discuss later on. But what we see here as well is that even though there is an increase here, say from the first quartile up till say around 0.4, but then from 0.4 onwards there was actually a decrease in terms of the wage gap. So in 1976 there was obviously no, as we call, class ceiling effect. And if you're going to look at all the years separately, so you start in 1976 up till 2022, I'm not going to do it over here, then you will actually see that at least until 2000, until the early 2000s, well, it was still the case that we saw more or less this picture over here, and only in the last, say, 10 to 15 years, the picture has switched to this picture that we have over here. That's not something that a lot of people have been doing research in, but it's of course interesting to see why we actually now recently have this relatively, well, big class ceiling effect, whereas it wasn't the case in 1976 and even wasn't the case in around 20 years ago. Well, we can also look at other pictures. Here we see, well, here we actually look at the developments over time, and well, what we do here is that we start here from 1976 up till 2022, which is of course about wages of 2021. And here we now have the quantiles on the y-axis, and we have two pictures, one for males and one for females. And now you cannot directly see anymore the differences in the distribution itself, but what we do see is that, well, we can now look at the different quantiles and deciles based on these different figures that we have over here. So we have here, we start here at the first decile, here you have the first quartile, median, third quartile, and this is the last decile. We have it for males and we also have it for female. One thing is immediately clear again, that for females, well, given the fact that the y-axes are exactly identical, we do see that females generally have lower quantiles than males. That's something that we have already seen before. But now it's interesting to focus a little bit more on the changes with respect to the years. Let's first of all focus on males, because of the fact that here males may actually be the most interesting to look at. And especially for males at the bottom of the distribution. Let's look at the most extreme case of D1, the first decile. Then we actually do see that the first decile, the wages of the first decile, have been decreasing actually quite a lot. Take into account, by the way, that these are real wages. These are wages based on 2022 dollars. So this is of course in log terms. But if you take the exponential, well, then you should not realize that, in dollars, people made 2.7, or the exponential 2.7 an hour in 1976. It was probably much less. We have, well, corrected this for inflation. But we do see that the real wages dropped actually quite a lot for the individuals at the bottom of the labor market, up till the, say, mid to late 90s. And then it increased a bit, but then, well, actually there was another time a decrease, especially around the period of the financial crisis. More recently, we do see that there is an increase with respect to the wages, even at the bottom of the wage distribution. However, the conclusion that we can make is that if we're going to compare this figure that we have over here with that figure that we have over there, that these men actually at the bottom of the wage distribution actually make, even in the year 2021, less than the year 1975. So taking into account that this is almost 50 years, and in all those 50 years, well, there were no real wage increases with respect to the males, and we're going to look in the period in between, then we actually do see pretty big decreases. Actually, we do not only see this with respect to the first decile, we also see this with respect to the first quartile. Even at the moment that we're going to look at the median, you should realize that there's hardly any increase, and there are big decreases over time. So if we compare 1976 to, well, the mid-90s, then we do also see that even for men at the median, there was a big decrease with respect to the real wages. We don't really see that at the moment that we're going to look at Q3, and even less at the moment that we're going to look at D9. At the moment that we're going to look at D9, there were really real wage increases over time. Well, what does that mean? Well, that means, of course, that men at the bottom of the distribution, they have decreased their wages. At the top of the distribution, they have increased their wages. So inequality, at least among men, must have increased. The moment that we're going to look at women, well, then we see a somewhat different picture. The main conclusion that we can make with respect to women is that, well, wages along the whole distribution have been increasing, especially at the moment that you're going to compare, say, 2021 with 1975. Even though, well, there were periods, especially at the bottom of the distribution, where you have slight decreases, or at least periods in which there have not been that big of increases. Well, and as well, then we see that at the moment that we're going to look more at the top, well, especially here at D9 and Q3, then we do see that at least since the, well, mid-80s, early to mid-80s, there has been quite a sharp increase with respect to the wages of the females. This definitely had an impact on the wage gap between women and men. But before we're going to look at that, let's look at the impact of inequality. These two figures show that essentially both males and females must have increased their inequality. And that's also what we see at the moment that we're going to look at the so-called D9-D1 ratio. That's nothing else is that I'm going to divide here the D9 with the D1 of men. This gives a little bit of an idea of how much essentially men make at D9 compared to, say, D1. It used to be for men around 3.2. That means that men at D9, so really at the top of the distribution, make about 3 to 3.5 times as much as men at the bottom of the distribution, but that has been increasing quite a lot. As much as that, well, since, well, now in 2021, there is even, well, it's around 5. So men make now 5 times as much at the moment that they are at the top of the wage distribution compared to the bottom of the wage distribution. And we do actually see that this increase has been almost monotonic. Only, well, in the last couple of years, so ever since the mid-2010s, we do see that there is a stop and maybe sometimes even a little slight decrease with respect to inequality. We see that that's more or less also true for females, but we should realize that for females, the increase has been a little bit lower. That's maybe not that easy to see from this picture, but take into account that at the moment that we're going to start here in 1975, then we see that actually inequality among females was larger than that one of males. And now at the moment in 2021, it was actually smaller. And then finally we can look at the wage gap. Well, maybe not that surprisingly, and something that we have already seen from previous pictures, we do see that quantiles, well, the gender wage gap actually has been decreasing over time. Especially it has been decreasing in the 80s and the 90s, not so much anymore since the year 2000, but still we do see that there was a decrease even since 2000 with respect to the wage gap. It used to be around, well, 60%, and nowadays it's about 20 to 25%. We do see that that's actually true for the whole distribution, even though, and that's not that great to see over here, well, this, say, the drop has been less important at the top of the distribution rather than at the bottom of the weights distribution. Before we can say something about estimation, it might be a good idea to say something about identification. Now, I'm not exactly sure whether you have heard much about identification before during your lecture series, but identification is, well, extremely important in econometrics. The reason why it's so important in econometrics has something to do with the most important things that we want to do in econometrics. What we typically want to do in econometrics is that we want to estimate objects or parameters. And the question, of course, arises how we're going to estimate objects in econometrics. Well, the answer to that is that we do not just, well, simply guess numbers, but that we typically estimate. And the question arises, how do we estimate? Well, that's based on data. So, and then a very important question that arises, even before we ask ourselves the question, how do we estimate, is can we actually estimate? And that question actually can be, well, asked a little bit better by asking ourselves the question, well, is the data that we have, has it enough information to be able to estimate the things that we want to estimate? Well, that is all about identification. And identification actually asks ourselves its question, well, suppose that we know everything that would be possible to get from the data set. Can we then estimate? And then an important question arises, what is actually the most that we can ever get from a data set, from our data? Well, in that sense, we should realize that we do know, of course, that data comes to us in a random way. So therefore, we as econometricians assume that data for us is nothing else as a random factor. It's a random factor of all the things that we are able to observe. So actually the question of what is the most that we can ever get from the data is the same question as what is the most that we can ever get from a random variable? But that's a question that we can already answer because of the fact that you have already heard, well, during, I suppose, the first year, that the most that we can ever get from a random variable is its distribution function. If we know the distribution function of a random variable, then we know everything about that random variable. So therefore, what we can say is that what we can ever get from the data is its distribution. It's not what we usually have because of the fact that nobody knows the data distribution. You only have a data set, which is something like a random draw from that particular distribution. But you do not have the distribution itself. You do not know how the distribution looks like. One important question that we can ask ourselves is, are we able to know the object, the real value of the object that we want to estimate, or the parameter that we want to estimate? Do we know that at the moment that we know the data distribution? If the answer to that is yes, then probably we'll also be able to estimate it. The answer to that is no. Well, then we will never be able to get that particular parameter because of the fact that even if we know everything about the data, then we still do not have enough information to get actually that particular parameter. So therefore, an important question always is in identification, well, if we know the data distribution, do we then know our parameter? Well, we can apply that for our case. At the moment, we would like to look at regression quantiles. With respect to regression quantiles, is relatively simple. You should realize that what is in our case the data distribution? Well, that's in our case we observe y1 and we observe x1. So the, well, conditional distribution of y1 condition x1, that is something that we do observe. At least that's the thing that is related to our data distribution. So the question arises, suppose that we know the data distribution. That's nothing else as assuming that we know this distribution that we have over here. Can we then say something about beta 0 and beta 1? Essentially our regression quantile. Well, that we can do in this picture. Again, we have here on the x-axis we have the different values of y, and on the y-axis we have our distribution function. The thing we can do is that we could look at the median. Then we do already know that the median is over here. But in this particular situation, we also know that the median, based on the assumption of regression quantiles that we have made in the previous slide, that the median is also equal to beta 0 evaluated in half plus x0 beta 1 evaluated in half. That's by the assumption that we have made in the previous slide. Question of course arises, well, what do we know? Well, we know the data distribution, as I already said. We know how this distribution looks like. But if we know the data distribution, then we also know its inverse, so we also know this thing that we've over here. But we do, of course, not know beta 0 and beta 1. We know actually x0. So based on this, what we can say is that we have one, say, equation, and we have two unknowns, beta 0 and beta 1. Well, from high school, you already know that if you have one equation and two unknowns, then it's impossible to know any of those unknowns. So based on this, you might say, like, well, probably beta 0 and beta 1 are not identified. But that's not completely true, because of the fact that what we can expect is that this x1, well, unless it's completely, well, deterministic, we should realize that we could actually have different values of x1. x1 could be equal to little x0 as we have over here. But as long as there's variation with respect to this x1, then x1 could be also equal to, well, for example, little x1. We might expect that that actually is going to affect the distribution, unless, of course, well, y1 and x1 are completely independent from each other. That implies, of course, that then in that particular situation, we are going to get a new distribution function. Suppose that this is now our new distribution function. We know, of course, that it could be anything, but let's just assume that we're going to get this particular situation over here. Then actually, based on this, we can calculate another time the median. Based on this is going to be our median. If we know the data distribution, then we also know this median. We also know that based on the assumption that we've made so far, that this must be equal to beta 0 half plus x1 multiplied by beta 1 evaluated in a half. But now we actually have two restrictions in two unknowns. So that means that we actually are able to know beta 0 and beta 1 right now. So then the only thing that we need to do is to, well, what we could do is that we could, well, subtract these two equations from each other. If we're going to do that, then we're going to get this restriction over here, and from that it's not that difficult, of course, to find out that beta 1 evaluated in half is nothing else as difference in terms of the quantiles divided by x1 minus x0. And because of the fact that the quantiles are known if we know the data distribution, and x1 and x0 of course are known as well, that immediately implies that we now can say that beta 1 is identified. Of course, based on the assumption that x1 is not deterministic. Take into account that you also need that in the case of a standard linear regression model, because of the fact in standard linear regression model, in order to be able to estimate the beta coefficients, we also need variation in the axis. And that's true here as well. So in that sense, there's not so much of a difference from the standard linear regression model. So the beta coefficients are identified as long as we have enough variation in the axis. I would like now to go on with the next topic, and that's the topic of estimation. Well, in order to estimate the beta coefficients, we can go back, well, some time earlier to the things that we have done today. And remember that we said that for any kind of random variable set, the quantiles can be represented by the arguments that is going to minimize this thing that we've over here. That is something that I already said before, and this holds true for any random variable, including, of course, a conditional random variable like y1 conditional x1 equal to x. So there what we can do is that we can now write the conditional random variable, the conditional quantile as being the argument that is going to minimize this thing over here. Take into account that even though this is exactly the same as we have over there, there are some subtle differences, of course. Here we have the conditional support of y conditional x. And in addition to that, we have here the conditional densities rather than the densities there that we have there. But take into account that apart from that, everything is exactly identical. Well, given the fact that we have made this assumption with respect to regression quantiles, namely that this quantile is equal to x times beta tau, you can also say that x times beta tau is going to be the argument that is going to minimize xb with respect to this number that we've over here. Take into account that here I still, well, more or less assume that xb is just a number. But if this is going to be true, well then for sure it should also be the case that we can actually take out the x, because x is just a number. If we say multiply that, then we can still actually minimize, but now with respect to beta tau. So what we could do is that we could also say like, well, of course this also implies that what we then want to do is that we want to minimize with respect to beta tau, and here we minimize then of course with respect to b. So we could also do this thing that we've over here. Well, now we are almost there. Now what we should realize that this actually is true for any level of the x's that we have. Not just for one particular x, but for any level of x, beta tau is going to minimize this thing that we've over here. So that means that we could look at x0 and x1 as we have done at the moment that we were looking at our, say, graphical illustration. But we can think of x as being continuously distributed, so then we can do it for any level of x. So that means, of course, that if we do it, first of all, if we simply do it for two x's, well then of course the sum of these criterion functions should also be minimized. If we do it for many x's, then we need the integral with respect to the minimization. So if this is going to be correct, then integrating over that criterion function should also be correct. So beta tau should also be the argument that's going to minimize this thing that we've over here. Well, the next thing that I can do is that I can rewrite this a little bit. Here we have the conditional density multiplied by the marginal. Well, that's actually also equal to now that we know that we can estimate the regression quantiles, the question arises, how are we going to be able to do so? Well, in order to understand that, we should remember that the quantiles of any random variable can be represented in this way that we have over here. That is to say that, well, any kind of quantile of this z can be written as the argument that is going to minimize this criterion function that we have over here. Well, then what we can do is that we can realize that this is of course true for any random variable, including of course a conditional random variable like y1 conditional on x1 equal to x. So there we can also write the conditional quantile of y1 conditional on x1 equal to x as the argument that's going to minimize this criterion function that we have over here. Take into account that even though the, well, idea is exactly the same, there are some subtle differences, of course, between this and that. That is to say that, first of all, we have here the conditional support, y conditional on x. And also here we have the conditional densities. But apart from that, the idea is exactly the same. Now we should realize that we do, of course, know that we have made this assumption of regression quantiles, that this thing that we have here at the left-hand side is equal to x times beta tau. So therefore we can also write it like this, that x times beta tau is going to be the argument that's going to minimize this criterion function over here. In this representation, we should realize that we see x times b as just one particular value, just the thing together. So xb is one particular number and we minimize that number and get x times beta tau. But at least assuming that x is going to be positive, we should realize that this is true. Then of course we can also get rid of the x and get exactly the same ID, that beta tau is going to be the argument that is going to minimize this thing that we have over here. So then this needs to be true as well. Now we can first of all rewrite this a little bit. First thing we can do is that we can realize that what I would like to have in the end is this one integral. We will see that that is going to be very useful later on. I just want to have one integral, not two of them. How can I get that? Well, one thing that I can do is that I can just try to get one large integral with respect to the full support of y conditional x. How can I do that at the moment that I have this one that we're over here? Well, I can do that by using an indicator function. I can integrate over the full support, but then I should realize that this thing over here is only allowed to be different from 0 at the moment that y is larger than x times b. So therefore I can simply write it like this term that we have over here. I can do exactly the same thing with respect to the second integral, but there I have to realize that then this part over here, well, should only be equal to, well, different from 0 at the moment that y is smaller or equal to x times b. So therefore I can write it like this. Well, and now I should realize that I now can actually take these integrals together. I haven't done it yet, but I'm allowed to take them together now based on the idea that I have exactly the same area of integration. So therefore I can take them together, take the tau's within the integral of course. In addition to that, I realize that I twice actually multiply here by the density function, so I can take the density function out of parentheses to finally get this thing that we have over here. Well, and then what I can do is that I can now realize that this is actually true for any level of x. So this is just not true for one particular x, but for any level of x. This, if I would like to get beta tau, well, what I do is minimizing this thing over here. So that implies, for example, that suppose that I have two different values of x, say x0 and x1, different from each other. Then at the moment that I minimize this criterion function with respect to x0, then I get beta tau. But if I minimize it with respect to x1, I also get beta tau. Doesn't really matter. Well, that implies, of course, given the fact that this thing that we have over here is going to be positive, that at the moment that I'm going to, well, add the two, say, criterion functions of x0 and x1, if I add them up together, well then at the moment that I'm going to minimize that criterion function, then I get also beta tau. Well, we can generalize that by saying like, well, I can even add up together with respect to all the x's. Assuming that x is continuously distributed, that implies the following. That implies that if I'm going to integrate over all the x's, this criterion function that we have over here, and multiply it then with the density function, and then I'm going to minimize this criterion function that we have over here, then I still will get beta tau. Well, this is very interesting because of the fact that then what I can do is that I can realize that this is the conditional density multiplied by the marginal. Well, conditional density multiplied by the marginal is always going to be the joint density. So I can even write it like this. But now we have something very interesting because of the fact that now what we have is, well, this is actually nothing else as a mean. This is a mean because of the fact that we now have an integral over, with respect to, of course, the joint density, with respect to this function that we have over here. So this is actually nothing else as a mean, and it's a mean, well, with respect to this function that we have over here. So in order to get it, we simply write here a large E, and then we are going to, well, we place y and x by the capitals. So then we get this representation over here. Well, this is actually very interesting because of the fact that now we see that if we would have known this function, this now is going to be a criterion function, a function of b, then if we minimize it, we get beta tau. But that's of course not possible because of the fact that we would only be able to know this function the moment that we know the joint distribution of y and x is from the data. So we only know it at the moment that we would would have known the data distribution. That's simply something we never do in econometrics. But it is still going to be valuable because of the fact that, again, as we have seen much earlier, what we could do is that we can try to estimate this mean that we have over here. Any kind of mean or population mean can always be estimated by its corresponding sample mean. How are we going to do that? Well, that's simple. No expectation, but summation. We sum over all the observations that we have, and we divide by the number of observations that we have. And we get then this criterion function that we have over here. Of course, this criterion function depends on a random sample, and therefore will generally be different from the mean that we have over there. It will be really surprising if this thing is going to be for any sample, it's going to be exactly the same as that thing that we have over there. But one thing we know for sure, and that is the law of large numbers. If n goes to infinity, then this thing will actually converge to that thing that we have over there. And that's true for any level of b. And that implies another time that we have here a very special and interesting thing. We have two functions. We have first of all a function that we do not know of, this function that we have over here. But one thing that we know for sure is that at the moment that we're going to minimize it, then we get beta tau. We have another function that we can at least estimate. It's different from the original function that we have, but we do know that at the moment that n goes to infinity, it's going to be exactly the same function, and therefore it has the same minimum. That implies, of course, that if we're going to define beta hat tau as being the minimum of this thing over here, that beta hat tau is going to converge in probability to this beta tau that is over here, hence it's going to be a consistent estimator. Well, again, this thing can be rewritten a bit. Again, as we have seen before, we should realize that this part, actually this part of the summation, is actually only different from 0 at the moment that we have an observation yi larger than xib. So instead of summing here over all the observations, we could also sum only over those observations for which yi is larger than xib. Then we get rid of the indicator function that we have over here. And we can do exactly the same thing with respect to this part of the sum in order to get now this criterion function that we have over here. This criterion function we can minimize, and you can actually show that this, well, minimization problem that we have over here can be written as a so-called linear programming model. And therefore we can use linear programming techniques in order to minimize this, say, function that we have over here. Well, Portnoy and Kumker in 1997 developed a fixed point method based on simulation methods, and most of the codes that is now available, for example in R and Python, but also in Stata, they actually use this method that they actually use. It's not very recommendable to do it yourself, to program it yourself, but it's very easy to actually use, well, code that is already available for you. That brings me to the asymptotic distribution of the quantum regression estimator. It can be shown that the square root of n multiplied by, well, beta hat minus the true level beta is normally distributed with a mean, of course, equal to 0 and a variance or a covariance matrix that can be represented by this thing that we have over here. Again, we have tau 1 minus tau, as we also had with respect to the quantiles. Now we get, well, this, say, second moment of x1 over here, and here, well, in the denominator we get another time a mean squared actually, and it another time depends on a density function and the beta tau. Question, of course, arises how we are able to estimate this. This is not that difficult to estimate. This actually is the most difficult part. What we should realize is that this again is a mean, a population mean, so it can be estimated by its corresponding sample mean. And the sample mean, again, summation over all the observations divided by n, gives us this thing over here. But of course we still have to estimate this density function that we have over here. Well, that can again be estimated by a kernel estimate. That's this kernel function that we have over here. Well, unfortunately this depends on the choice of the kernel and the bandwidth. That's the reason why a lot of people actually don't use this. even though it's pre-programmed in Python, Stata, and in R. But another way you can actually do this is simply by using bootstraps. Then the implementation. We can implement this in Python, we can implement this in R, and as well as in Stata. Stata is very easy. Then there is a command called qreg, but I'm not going to talk too much about that because of the fact that I like more Python and R. Let's first start with Python. I'm not sure how much you know about Python, but first of all, what we usually do is that we import a couple of different libraries. Pandas is a very nice library, which is about databases. NumPy is also very useful. And then we have, in this case, the most important one is the stats models, because of the fact that that gives us the opportunity to do quantile regression, especially this one that we have over here. First thing that I do is that I introduce an array where I define the different levels of tau from 0.1 up till 0.9, and then I do the different quantile regressions. And well, this is actually the main statement that we need for quantile regression, but then we also do the model fit that we actually have here in this tau that we are going to do the for loop with. We calculate the parameters, or we get the parameters, and we have here the standard deviations, and we store them in result and result1, and we finally print out the summary. But we can do exactly the same at the moment that we're going to look at R. Well, then also we have to introduce some libraries, as they are called right now. And well, then the first library that we have is Haven. That one is actually only used here in order to be able to include this Stata data set. And the other library, QuantReg, well, that one is in order to do the quantile regression, which is now called RQ. Well, the rest is exactly the same. Here we define the different levels of tau. Here we do the for loop. We do the quantile regression over here, and we store the coefficients first of all in param and SD as the standard errors, and then we store them in result and result1. And here we summarize. Well, we actually print out the results. Then we get the following results. I'm going to look here at different kind of regressors. First of all, gender, whether somebody is a woman or not. We have here the different levels of education, high school graduate, some college, and college. Well, the left out variable is, in this case, so the left out category is now not having a high school diploma, so a high school dropout. We have here different kind of regions, south, central, and west, where here the northwest is going to be the left out category. And we have central city, metropolitan, whether you live in a metropolitan area. We have H and H squared, and we have some ethnical background characteristics, non-white and Hispanic. Coming back now to gender, well, first of all, something about a constant. Usually the constant is not that interesting to look at, but here it is because of the fact that, well, generally at the moment that we're going to do quantile regression, you should realize that the conditional quantiles increase with tau, and that is also the reason why we always see that the constant actually increases with tau. Then gender, well, with gender, it doesn't come as a big surprise that we find that gender has a negative impact. Generally, it's about 23%, but it decreases for the highest levels. Also, that is probably not that, well, not that surprising given the results that we have seen before for 2022. Then, in addition to that, well, at the moment that we look at education, then we see generally that, of course, the higher your education level, well, the higher is going to be your wage along the whole distribution, where the only exception is, and that's a little bit surprising, that having some college is actually worse for your wages than at the moment that you only have a high school diploma. Another thing that we actually see is that, well, the returns to education are increasing with tau. It's especially true at the moment that we're going to look at college, but it's also actually true at the moment that we are going to look at high school graduate, and in some sense also for some college. Well, there's not so much to say about region. More interesting is to look at central city. Actually, central city doesn't seem to do anything over here, and that's maybe a little bit surprising, especially for people from Europe. what we should take into account is that living in a central city is actually not that attractive. Central cities in the US, generally, apart from Washington, D.C. and New York City, should realize that central cities in the US are not that attractive. And that's the reason why you actually, unlike what you see in Europe, most people don't want to live in a central city. And that implies also that at the moment that you're going to look at the individuals living in a central city, unlike in Europe, where, for example, in London, well, people that live in central city will actually have a lot of money because of the fact that otherwise they would not be able to buy apartments over there. That's actually not true for the United States. That doesn't mean that people in the United States do not want to live in, say, in cities, because of the fact that you do see that metropolitan areas actually increases the wages by quite a lot. And that's also, again, increasing with respect to tile. That's true, of course, because of the fact that people with money can actually afford to buy a house in, well, relatively expensive metropolitan areas, but it's also the other way around, of course. In metropolitan areas, you have more jobs available, more well-paying jobs available, and that also has a positive impact on the wage. Age is having a positive impact on the wage. Well, that of course is related to the fact that we don't have experience over here, that more or older individuals typically also more experienced, but we do not see that much, well, we do not see that much of a difference along the distribution. We do see that the relationship is not linear, but we don't see anything along the distribution. Then non-white, well, again, it doesn't come as a big surprise that actually does have a negative impact. More as a surprise is that it is less important at the moment that we're going to look at the higher quantiles. It might be related to the fact that non-white is of course very broad. It includes also Asians, and that might be the reason why we have here at the upper part that it becomes less important. Hispanic, well, for Hispanics we also see that there's a negative impact, and that actually doesn't seem to change that much at the moment that you climb up the job ladder.